Good day and welcome to another unit of Physics 191 Experimental Physics 1. In this unit, we'll be considering viscosity and surface tension. At the end of this unit, you should be able to use Stokes' law to determine the coefficient of viscosity of a particular liquid, considering glycerol, by timing the fall of ball bearings through the liquid. And finally, you should be able to measure the surface tension coefficient of water by observing the rise of water in a capillary tube. We are starting with the viscosity. And the aim of this experiment is to use Stokes' law, like I mentioned, to determine the coefficient of viscosity of glycerol by timing the fall of ball bearings through this liquid. An application of Stokes' law shows that terminal velocity V of a sphere of radius of material of density rho, we are using V to represent the terminal velocity, and we are using rho, as you can see, to represent the density of the material in an infinite reservoir of liquid of viscosity eta. That symbol is called eta, is given by this expression: 4/3 pi a cube rho g equals 4/3 pi a cube sigma g plus 6 pi a eta v. And I will explain what each of these symbols stands for. The sigma is the density of the liquid, the rho is the density of the material, g is acceleration due to gravity. And if you want to find the eta, which is the coefficient of viscosity, you have that expression 2/9 a squared multiplied by g into bracket rho minus sigma over v. Now, in this experiment, you are to measure V by timing the time t for the fall of the sphere, that your ball bearing, through a distance d in the liquid. You have a liquid in a container, maybe a measuring cylinder or any container. You drop a ball bearing, a sphere that is spherical in nature. You drop it in the liquid and you time the fall from the top of the liquid to the bottom of the liquid. That is what I mean by timing the fall of the sphere of the material. Now we can then write that a square equals, that is the acceleration of the fall, equals 9 multiplied by eta, that is the coefficient of viscosity, multiplied by d, the distance of the fall, divided by 2 multiplied by g into bracket rho minus theta minus sigma multiplied by t. So if you have this expression, you can easily get the acceleration of the fall. Now you can plot a graph of square of the acceleration against the inverse of the time. Square of the acceleration on the vertical axis and the inverse of the time on the horizontal axis of your graph. And with that, if you linearize the equation above, if you linearize it, you are going to have the slope, that is the gradient of the graph, to be equals to 9 multiplied by coefficient of viscosity, that's eta, multiplied by d, divided by 2g into bracket rho minus sigma, that is the density of the material minus density of the liquid. Now, the second aspect of this discussion is on surface tension. The aim of this experiment is to measure the surface tension coefficient of water by observing the rise of water in a capillary tube. You have a capillary tube and water is poured in it. The rise of water in that capillary tube can help you to know the coefficient of surface tension of the water. And the theory of surface tension shows that the liquid of a particular density, if we use rho to represent the density, will rise to height d in a capillary tube of ball radius r. Now surface tension, gamma, as you have it, we use gamma to represent it, is obtained by saying gamma equals to half of r d rho g, half multiplied by r, the ball radius of the capillary tube, multiplied by d, that's the height, multiplied by rho, that's liquid density, and finally multiplied by g, acceleration due to gravity. With this, you can determine the surface tension of a liquid. So what I'm saying in essence is that if you have a capillary tube, a water is inside it, and you want to determine the surface tension, the coefficient of surface tension of that water, once you get these parameters, you can conveniently put them in this formula and get the surface tension of the liquid. So in this unit, you have learned how to use Stokes' law to determine the coefficient of viscosity of glycerol, using glycerol as an example. Any other liquid can be considered also. by timing the fall of ball bearings. And finally, you have learned how to measure the surface tension coefficient of water by observing the rise of water in a capillary tube. Thank you.